Today's demo is going to work with a lot of data. And what I'm going to do is show you how to run zonal stats, or basically a spatial join, for a global raster dataset on every single building in the world from the Overture Maps dataset. What we'll end up with is a map that looks just like this and a dataset that covers for all 700 plus million buildings in the world. So today I am actually in San Francisco. As you can see here, this is a real space that I'm in at the Wherobots offices here in downtown San Francisco. So it seemed appropriate to take some time to film a demo that I actually posted in a short a couple weeks ago and actually show you how to do this in Wherobots to actually do this very large spatial join and run it in just a handful of seconds. So that's what we're going to take a look at today. So first things first, let's take a look at the data we're going to be working with. The raster data set that we're going to be working with is the global 30-meter raster height above nearest drainage data set. It's also called HAND, if you want to call it that, so I might refer to it as the HAND data set from this point forward. What this data set does is it determines for every pixel the height above the nearest drainage point. So a drainage point might be something like a body of water, a pond, river, stream, anything like that, and how high that nearest pixel is above that specific area. Now, you can see a view of what this data set looks like here on the Google Earth Engine Community Catalog. And if you want to, you can actually open this up in a Google Earth Engine viewer and take a look at it there. But this data set covers data globally. And of course, we want to be able to access all of that data and do so efficiently. Now, transferring all this data to your computer or to some other service or location would take a really long time. It's quite a large data set. What's unique about Wherobots is it allows us to connect to what's known as out-of-database rasters, or raster data that's stored on a separate service, in this case, AWS S3. We can do so by using the stack, or the spatiotemporal asset catalog endpoint, to retrieve that data. So here we can see some of this, or a quick view of this data, in the Stack browser itself. That actually shows us what is inside the data set and some of the different data that's there. Over here, you can see basically the coverage of the data set, which is the entire globe. In reality, it doesn't cover everything. It only covers areas that have land in them, so nothing over the water, which is nice. We don't have to worry about that. And then it gives you the cloud-optimized GeoTIFF tiles here. So if I go a few levels deep, you can actually take a look at what the data looks like. Generally, what's easier to do, though, is to get a spatial filter. So we'll do that right here and just into a specific area. So we only have a few tiles to look at, and we'll just go down here and we'll submit that. And then we should just get a smaller subset of that data, which is here. Now, as you can see, we can see where the data is here. You can actually download that, or we can actually show that on the map. So that might take a minute to load up just so you can see the actual data. And the data is actually stored on an HTTP URL, which we'll talk about in a minute. To work with this in Wherobots, we need that in an S3 URL, which we'll actually go through in the demo, but that's not too hard to do. But here you can actually see the raster data. And you can see here these darker areas are of higher elevation. The lighter areas are, of course, lower elevation or lower to the drainage point. And this area here that is in the lightest area, which isn't quite showing up right now, is the Mississippi River. So that's obviously going to be your 0 level drainage. Now, to get this data, we want to work with the stack endpoint. Now, the spatiotemporal asset catalog comes with both that viewer level that you can actually pass that into, but there's actually an API where you can get access to this data. There's some descriptions and things like that. But what we want to look at are the items. So that we can show here. And this will actually show you a specific set of those individual cloud optimized GeoTIFF tiles, and it returns it as GeoJSON. So as you can see here, it has some of the features and then the actual geometry that bounds that specific tile or that subset of data. So that's what we're going to want to do. So let's go ahead and jump into Wherobots to get started and actually start to work through some of this data. Now, if you haven't set up a Wherobots account, you can actually do that here. You can go ahead and sign in or just try Wherobots if you haven't. Fill this out, and then you'll go ahead and get your account set up. There's community edition accounts as well as paid accounts that you can get access to, and different levels or tiers of compute, which you can use as well. So once you're signed in, you can start one of the different compute levels here. You should be able to work with the general purpose. You could start that at tiny or small, medium, whatever you want to. Of course, as you go up in different levels, you'll get additional computing power. So you can start with whatever choice you want. So once you click on that, you can give it a name and go ahead and click start. That will show up down here, and then you just hit open, which will open the notebook interface. Now I've loaded in the notebook here. I'm going to share the notebook as well as some of the data sets so you can actually make use of this yourself. So once I have that hosted, I'll pass in those links so you can try this yourselves and run this in Wherobots. As well as if you want to run in the community edition, I'll give you like a bounding box you can pass in to make that a little bit smaller should you so choose to do that and just want to run it on a subsample of data. So the first thing I want to call attention to is here, this configuration. So we're building what's known as our Sedona context, which is basically the structure that we're passing to our compute environment that tells us some of the different things. We give it an app name here. I'm calling it Overture Elevation Join. And I'm passing these credentials that actually allow us to access that specific bucket in AWS. GLO30 hand is the name of that bucket. And I'm also allowing it to use the anonymous credentials provider. Now, because it's a public bucket, you can access it anonymously. You don't need AWS credentials to do so. This allows us to do that and gives it the context to actually go ahead and do that. And once that's all set up, I have my Sedona context. You'll see us use this object word or these keywords Sedona in several different places to do that. Now, the tricky part about this is actually not getting the data from the stack endpoint. It's actually the fact that the stack endpoint has a limit about how many things it can return. So in this case, that limit is 10,000 objects. It has more than 10,000 objects, and you want to be able to basically get everything that's in there. So what I had to do was basically split into 4 bounding boxes, the entire globe. So there's the northwest, northeast, southwest, and southeast quarter of the world, and I split it up within that to go to each of those. So then what I did was basically fetch the GeoJSON from that API, which is the same one that I showed you earlier, and return or save that GeoJSON file. Then the next thing is just to go through all of those GeoJSON files and turn them into one big GeoJSON file, which is the only thing that I'm doing there. And then save that and turn in all the features to the GeoJSON. Now, the other tricky thing is if you're not familiar, GeoJSON is like a very odd nested JSON type, which means it basically saves everything in kind of separate JSON objects, not in like lines as you would in a normal tabular format, or how most JSON works, GeoJSON works the opposite. So we have to turn it into this new line delimited JSON format, which I just created a simple function to do that. You could do that in GDAL or through other tools if you really wanted to. There's no right or wrong way to do that, but certainly easy to do. And that's just what I've created here. And then I'm just saving that file or that GeoJSON locally. Now in Wherobots, you do get access to some managed cloud storage or S3 storage as a part of the platform. And what I'm doing is I'm just retrieving that user path here. So you see I have my bucket, my customer ID, and some different elements that give me that specific bucket that I get access to as a part of my Wherobots account. So what I'm going to do is actually push that JSON file to there, the new line delimited JSON file. And the first thing I'm going to do is just show that on the map. So to read a JSON file, all I have to do here is read in the Sedona read format and then GeoJSON. And then I'm just loading that URL that I uploaded it to earlier. It's far easier to read it from that cloud storage than it is locally. So basically, you're always going to want to push that cloud storage. It's faster to do the reads and ultimately easier, more secure, all these different things that you want to be able to do. So when it's in S3, it just works better and you get access to that as part of the platform. So what I'm going to do is I'm going to go ahead and read that GeoJSON file that's now contained in this object df or the data frame here. And we're just going to show you what that looks like. I'm going to pull in the Sedona Kepler integration, which integrates Kepler GL maps experiences into Apache Sedona and in turn Wherobots. And I'm just going to add that to a map here so we can quickly see all of those individual files on the map. Okay, so as you can see here, just like we had in the maps that we were showing on the Stack browser, you can see this is an individual tile here, and you can see in the ID, we have the ID, which has north 37, west 123. So I think it's basically the globe sliced up into decimal degrees of 1 by 1, more or less. And we can zoom out and you can see how that coverage goes over the entire globe, but just the areas that have land. We're not actually going into any areas that have water or anything like that. So any area that has even some coverage in land will actually get covered here. So those are all the individual tiles of data in that cloud optimized GeoTIFF that we're going to be pulling in. So as I mentioned, to work securely, we actually need to read the S3 URL. And for some reason, I don't know why, but this stack endpoint points to HTTP URLs, which is not going to work for what we want to do. So this is just a function to modify that path and turn it into an S3 URL, right? So it's that S3 URI, I should say. So that's what we did. And you can see here that it turned it into that S3 URI, which is exactly what we wanted to do. So this is all the data extraction that we've set up. And now we'll get into the part where we actually work with Wherobots and Sedona to structure our data and actually run the analysis we want to run. So one of the first things I want to point out that I think is particularly unique, and I've talked a little bit about this before, is the ability to create an out-of-database raster connection. You can do something similar in PostGIS as well. And what's really great about this is that I'm reading raster data from cloud storage, like you can see here, without actually connecting to it at all. I'm not actually transferring that data. So I'm creating sort of this remote connection that references that S3 URL or that location where the data is, but I'm actually not, reading all of that data or transferring it in, which would be gigabytes or more of data, lots and lots of data movement, which you don't want to do. So that's what we're going to do here. It's very effective, and especially when we're actually running the analysis, it allows us to reference just the parts we need, and particularly even better, just some of the pixels that we need. So we're only materializing that little bit of data we actually need to pull into our analysis to go from there. So that's what we're going to do. I'm going to create a raster, or this df rast with a new column called raster. And I'm going to use the expression rs from path, which is allowing me to pass in that specific URL or that URI, that S3 URI that I wanted. Now, another key point within the distributed computing within Wherobots is this concept of repartitioning, right? The best way I have to think about this is that effectively, if you think of your data in a distributed computing system, in a normal computing system or on your computer, you're running with like one node of data, right? Or sorry, one node of compute, and everything runs in that. In a distributed system, you're splitting that up amongst multiple workers, right? And multiple nodes, as it were. The partitioning helps distribute that data to those multiple nodes and allows it to read across all those different areas much faster and more efficiently. So that's what we're doing here, is just adding that partitioning in. It's going to speed everything up downstream. Other systems kind of handle this for you in different ways. If you work with like other ones, you still even have to do that in some of these other systems anyways to make it really work well. So we're just adding that kind of partition component here. Now, the other thing we want to do is that if I were to load this in, this would be one giant out-of-database raster reference. So it'd be one single giant GeoTIFF. And since the data is already divided neatly into these sort of tiles of data from the cloud optimized GeoTIFF, we want to take advantage of that. And basically what we do, we're calling exploding that out back into those individual tiles. And we know that the tiles are within the 512 by 512 system. So it's 500 pixels by 512. So we can split that out, which will also add another element here that we can split that raster out. We're going to drop that raster column, and then we have an even faster way to reference those tiles. So it's just a little bit of data prep if you think about that. We're doing the repartitioning, and we're doing the exploding of the tiles the raster tiles that we can do here within that cloud optimized GeoTIFF. So we're taking that reference and just blowing it out a little bit to make it a little bit bigger. We're going to create that as a view. So that effectively, within the context of this notebook, creates a view or a data frame that we can reference in Python or in SQL in any way we want to. And what I'm going to do is actually store that as a table in Wherobots DB. Now, Wherobots DB is kind of like a database, but it's a sort of a newer concept. I've only talked a little bit about. I've talked about data lakes. I'll put a link to that video up here, but it kind of uses the lake house architecture, which is a lot of terms. So when you think of a data lake, it's a collection of data on a storage bucket or a cloud storage system like Amazon S3, Google Cloud Storage, there's DigitalOcean, there's Blair R2, there's lots of different ones that you can use. And that's basically what a quote data lake is, right? The data lake allows you to store lots of data. The data warehouse allows you to organize and structure that. And that allows you to add the concept of treating it like tables, which also allows you to treat it just like a table in, let's say, PostGIS. You can add to the table, you can subtract from the table or remove rows, you can delete it, you can make new copies of the tables, everything like that. But what's actually happening is it's not tables in a database, it's actually just cloud storage and Parquet or GeoParquet under the hood. What the difference is that allows you to a sort of a metadata layer that allows you to track all those transactions and changes to the data set. In this case, that is Apache Iceberg. So if you want to take a look at the Apache Iceberg website here, we can see a little bit about this. It's the open table format for analytics datasets. You can see here it has expressive SQL that you can write, but it's actually writing just again to your cloud storage, which makes it pretty nice. You can change your tables, alter them. There's hidden partitioning, so there's an extra layer of partitioning that helps with reading or querying your data, and then you can move and roll back that data. So it has those time travel kind of reproducible queries that allows you can see the version as of this specific time and place and things like that. So all of those pieces are really nice. The problem, if there is a problem, is that Apache Iceberg doesn't support geography or geometry data. So Wherobots, we actually worked on solving that, and we're actually working on porting that back into Iceberg. So hopefully that will be there soon. But actually moving that back in and then allowing anyone to use that. For the time being, we have a separate version called Havasu, which has support for the geometry object in Iceberg. So that's all I'm doing here is I'm basically creating a table, but it's ending up on cloud storage. So just to show what that looks like, I can go into my managed storage here in Wherobots Cloud. And what you can see here is I've gone into wherobots.mat, just as you see here, and then I have that hand 30 layer here. This is where I've stored my data table. And so that will essentially show me under the hood what's happening and how all that data is referenced. So you can see there's two components here. One is the data, and then one is the metadata. So we can take a look at both of these. Let's open the metadata first, which is basically where that table schema, the transactions, all of that stuff I talked about from Apache Iceberg, that's going to be stored here. So you can see it's just a set of files in the cloud storage system that's sitting there. And you can see here's some of the metadata. You can see when there's changes and things like that. So there's all of this data here that keeps track of that table. If you want to take a look at it, you could download these files and do that. And then if we go backwards, the data is actually just sitting here. So you can see here that it's basically just a bunch of Parquet files, and they're split up by sizing, and there's some different elements, but this is the under the hood partitioning. It's really not readable to me or you to know what's in here, but this is the under the hood partitioning that's just handling all of that for us, which makes that really nice. So going back to the notebook, I'm setting that up here, and then now we actually get into the analysis. So what I'm going to do first is create a buildings data frame, and this is all the buildings from the Overture buildings data set. And I'm just going to grab the ID, the height, and I'm going to create a very small buffer around the geometry. So 30 meters, because I want to ensure that it's capturing or sitting across at least a pixel. So it's a 30-meter pixel. And I want to also get some relative averages for that building, so it kind of smooths the data out a little bit. So that's what I'm doing here. And you can see that I've pulled that in. We'll actually go ahead and start running our cells now, so we can do that. And you see here that I have a building count just about, if I do my math right, 785 million buildings globally. So that's what I have here. And I'm going to load in this, I'm calling it a DEM. This is the hand data set, but I'm basically loading that in here. And then I'm going to split up the partitions to do that across the raster file that I'm running here. So let's go ahead and run this. And then I'm just, like I said, I repartition and I'm going to create or replace that view here. So I have that temporary view stored in the context of this notebook that I can go ahead and use. We'll do the same for the buildings. So we'll do some of that partitioning here. And then the last bit I'm going to do is I'm just going to cache those two data frames so they're referenced in the notebook, and they're basically stored within the context of the notebook. So then we have something that probably looks very similar, which is just some basic spatial SQL. I'm going to select the ID and geometry from table A, which is the buildings partition data set, which I've cached, and I can now, because I've cached it, I can use it in the query. And then I'm going to use the DEM part, which is R. So I'm going to do the zonal stats here. And this is a function, a raster specific SQL, raster spatial SQL function that exists in Apache Sedona and then in Wherobots. And what I'm doing here, this is the signature of this function. So I'm pulling in the raster, then the geometry, and then I'm pulling in the average. I want to get the average of that specific raster, and then I'm setting that to false. We can go ahead and look at the specific function over here. So here is the function itself, and you can see here that there's a few different things we can do, but basically what I have here is the integer of the band, which is 1. There's only one band in this data set, the stat type, and then to exclude no data. So if I want to get rid of no data, I can do that. And lenient the function will return null if the raster and zone geometry don't intersect. So that's to basically get around that. We added that little buffer in there. So that's what we're doing here. And you can see here's the structure of that function, which we do over here. Now I'm also adding in this like spatial filter, if you think of it this way, this where filter, to make sure that to find everything that intersects. And this is basically an element that is optimized in Wherobots, that's specific to Wherobots and the compute infrastructure that we use. Adding that in allows it to read the spatial predicates or the spatial pushdown or the spatial relationships. And that speeds everything up and makes it a lot more performant than anything out there. And this is the really fun part that I've had so far about this, is learning these little things that I wouldn't normally write in Spatial SQL, but just adding this in adds so much speed and performance to what we're trying to do, and speeds it and makes it up, so fast. So that's kind of, you can learn a little bit more about here if you want to learn about the spatial pushdowns and doing these different things. It allows it to speed everything up and read it a lot faster and do what we want to do. So I won't get in too much into that right now. So what I'm going to do is, you can see here, I'm going to join this. I'm going to create the temporary view again. I can read, it's going to tell me, it hasn't run the query yet, just so you know. It's going to tell me I get an IG and a geometry and a number that tells me the elevation above the drainage. And you can see, if you want to get really into the weeds here, the query plan, you can see all the things it's going to do. Here's the range join, and you can see that's where it's actually running that RS intersect. So it's doing those spatial operations right at the beginning, and then using that to make things so much more efficient, which is the really optimal part of what we're doing at Wherobots, which is speeding up everything that happens from there. So now it's time to actually run this thing. We'll go ahead and run it, and just watch that run, and I'll cut the video and I'll come back and you'll see the results here in a second. Okay, so this just finished up, and you can see here it took about, it says 332 seconds. So if I do my math, that's about 5.5 minutes. Now, I'm actually running this on one of our smaller compute clusters just to show you that it still can. I ran it on one of our larger ones and took 96 seconds. So depending on how fast you want these results, you can get them. But even so, one of the things that we're looking at is we can actually run these things so much faster and even 20 to 60 times faster than, Apache Sedona on any other environment. So even on a, pretty small compute cluster, you can still get pretty remarkable results. And that's kind of what I want to showcase here. So even though this one took 5.5 minutes, I can get it all the way down to 1.5 minutes if I really, really wanted to. But for something like this, where you're doing a batch processing, waiting 5 minutes, is still very fast compared to, if you multiply that by 20 or 60, it's going to take you a long time. So then I just did, I just showed the results here. So I just actually wanted to show a few results, and I'm just doing a bounding box around an area where I live, so I could, kind of see that, doing all the same steps. So doing the SQL here, you notice I'm just adding in the here, I'm joining that, doing the same query as above, but just to that other data frame. That query for that small area took about 19 seconds. And then you can see here, this is our results. So basically, I know these lighter areas are going to be of higher elevation. So you can see here, this is 12.7 meters above the nearest drainage. This is going to be 0.64. And these lower areas, these blue areas, are going to be closer or lower to a drainage point. And you can actually see some of that on the map. So if we look at any of these low-lying areas, you can see this is a pond down here that's actually lower to the drainage. You can see this is basically at the same level of the drainage. You can see here for some of these very low-lying areas, here's another pond. That's basically lower, and you can kind of get a sense of that elevation here. So you can see some of these areas that are, there's probably some sort of drainage here that you can't necessarily see. But as you get, obviously closer to some of the coastal water or some other features like that, you can start to see that. So basically, if you look at this in aggregate, these lighter areas are going to be less susceptible to things like flash flooding. And that's really what this is showing here, is that if there's a sudden influx of water, these darker areas where the water is likely to pool or collect. And that's something that, of course, matters a lot. Actually, in this area where I live, we've had lots of flash flooding in the past year with just massive amounts of rain and rainfall coming down and just inundating, where we live. And there's, of course, pools in different areas, but I know exactly in some of these areas where the water collects, and it basically matches up to this map, I should say. And that's what's cool about this, is I can actually do this and then do it for anywhere on the globe, right? I may not want to visualize all that necessarily, but now I have access to that data. And since I'm storing it in the Havasu iceberg format, I can query that and let anyone access that. And even more so, there's a lot of other tools that can access that table format. So once I've created that table, things like BigQuery can read it, or DuckDB, or Snowflake, or many other different tools that can read that iceberg specification. Now, since it doesn't natively support the geometry, it'll get pulled in as a well-known binary, so you have to do some of the transformations, but it basically gives you that whole table spec that you can use, which is great. So what I'm going to do with this book here, I'm going to share the notebook. I've annotated it, cleaned it up, made it as usable as I can. I'll share that so you can use that. I'll also share the underlying data in that table format so you can use it as well and do some just analysis on top of that. And I'll push that to maybe a Source Cooperative or something else, so you can actually take and make use of this and do something interesting with it. So yeah, I hope you enjoyed this tutorial. I had a lot of fun putting it together to really push the bounds of what I'm able to do and just show kind of the performance and speed. Even on our on a smaller compute cluster, you get to choose, like I said, there's lots of different compute environments that you can use. So it's not like, you can pick what you need and scale to what you need to. So, and even on our community cluster, you can still do quite a bit of stuff with this. So I hope this was helpful to help you kind of understand some of the elements that are at play here, from the out of database raster, the spatial data lake or lakehouse concept with Havasu, Iceberg, integrating with some of the data sets that we already have integrated from Overture Maps. And then I hope to do more things like this and then publish more of this data to make it really useful across not just our platform, but many others as well through Source Cooperative and the cloud native format. So hopefully this is helpful. Let me know if you have any questions and comments. If there's other videos you want me to do like this, I'm happy to do so. But until next time, I'm signing off from cloudy San Francisco and the Wherobots office is here in San Fran, but I will see you next time, probably from my basement studio back in New York. So take care.